Swayam Prabha. Digital India. Educated India.
Welcome back. Just a quick review of what we have been discussing. I'm talking about what are some common type of characteristics that the systems show. We discussed a little bit about complexities in terms of how they're difficult to understand, difficult to predict. There are too many players, too many variables, too many interactions. They are dynamic. Systems exhibit not a continuous behavior, same behavior over time. It actually changes over time. They are a lot of time governed by feedback loops. We have looked at some examples, but we will also look more specifically. Often these feedback have something called delays, that their effects are not visible immediately, and that actually makes it much more complicated. We will also talk a little bit later about the nonlinear behavior, how it's not always an incremental 1 unit change in input will not always result into 1 unit change in output. So how does it matter? Why it matters is all we will look into later. And every action has multiple reactions within the same, multiple reaction across different stakeholders. So idea is, how can we then become better at developing solutions using some of these principles, recognizing all this complexity. That's the precise idea that we are getting some idea. Of course, it's one thing that I want to become very clear is there is a art in it. Although always there's an element of art in systems thinking, is that you may be familiar with terminology, technology, technical terms, but the more you practice, the better you become, kind of thing happens. So you can engineer, and even the break I was looking at some of the example, you can engineer it a little bit, but of course it takes long efforts to sometime practice it. And even now I was exposed to this topic back in my PhD first year. That's when I started exploring, and still sometimes I make decisions and then I realize, this I could have easily seen, like why didn't I think of that? So it takes long practice. It's not like, okay, you take one lecture and you become a systems thinker. Don't claim so, please. Because there are people who claims like that, and that is even more of a big problem. So that's also a part of systems problem. But let's continue on some of these things, right? So system commonly exhibits some properties, and we are going to think about them a little bit. One common thing that a lot of socio-technical systems we are dealing with is delays. I'll give you a very simple example of a delay. You are driving a car, looking at different objects. You are able to control your speed, maybe apply brakes, maybe apply accelerator, decelerate, change everything. Suppose you were living in a world where, and what is the reaction time of a human? Do you guys know? Average human, roughly 0.2 seconds. As per IRC code, let's Indian Road Congress code says 0.2 second is the average reaction time. Suppose your reaction time became 1 second. Would it be possible for you to drive the vehicle? You would have seen an object, and fastest you can react to it is only 1 second later. And that too, when you think that I'm going to apply brake, there's another 1 second for you to actually apply brake. What will happen, right? So delay, it's a very simple example, but delay can create chaos. And here at least delay is visible. A lot of time in the complex system, it's not even recognized that this is happening because of somebody did something 30 years ago, 20 years ago. So delay is not, of course, to put blame on previous generation. That's not the purpose, but to realize that sometimes the impacts are not visible immediately. Why it matters? Sometimes if the solution is genuinely good, but there are delays in its effect to be visible. For example, you know that this solution is going to be quite effective in the long term, but it takes time for these effects to be visible. People may actually lose trust that, hey, this thing is not working. Why are you keep pushing money on it, right? So delays can actually make your good decisions also reverse to the bad ones. And of course, sometimes in order to understand the problem, it can also create problems, right? So because of the delay, we sometimes end up doing things too much or too little. We end up giving too much braking compared to what was needed versus what maybe sometimes we do not apply enough brake and because we do not anticipate, because there's a huge time perception delay in terms of like what you think is the current state of the system versus what the current state of the system actually is. And delay is everywhere. Like when I ask you a question like what is the population of India right now? Do you know what is the delay in estimating population for a country like India? When was the last census got done? 2011, right? So for past 10 years, we don't even know, we have not measured, and even if you make a real-time judgment of anything, still delay is not only about collecting information, delay also happens in analyzing the information, delay also happens in taking a decision out of it. You may be sitting on collecting data, those who are doing PhD or doing some master's project, maybe data collection you finish in first month of your study, but it takes a long time for you before you can graduate, partly because there are many factors, partly because it takes long time for you to actually analyze the data. You have been sitting on the data, it takes time for you to see what is saying and doing some decisions on that. So there are delays actually everywhere. Some example, virus exposure versus getting sick. You may have been exposed to a virus maybe a couple of days ago, but only the symptoms are now visible, and only when you see the symptoms, you actually take medicine. By the time it might be too late in certain cases, right? You may have already been overexposed and the body is not showcasing symptoms and so on and so forth. So delays, in that case, you taking an action related to consuming the medicine is actually not on time when it should have been, because you don't perceive your symptoms unless certain time has passed, right? Eating food and learning that stomach is full, does that happen? One chapati above, you are thinking, I can have maybe a little bit, and in middle of the half chapati, you are like, I'm suddenly full. That perception, you end up overeating because of this. So this perception delay causes there. Flushing into septic tanks and groundwater pollution. If you septic tanks, I'm hoping all of you know, this is where the sewer connection is not there. This kind of a primary treatment that is typically available on a single household. You flush once, you will not see any effect on your environment close to you, right? But soon, if you keep on flushing for longer time, you will see suddenly there is a lot of pollution around your house, and that's become perceivable, that becomes visible only after some time. Pesticide exposure and illness, tap temperature control or whatever, many things, production and quality inspection in construction languages, right? So delay actually affect twice. One is it can affect the identification of the correct problem, because you may not know why these are happening. Also, it can actually affect the response of your system. It can actually either create extra response, less response than needed, and maybe you will not be able to control the thing in the way you want to control, right? So it misleads us into taking more immediate, and also it causes, because people find it very difficult to believe that today's event is happening because some decision was done 10 years ago. It's very hard for humans to actually think about that. We tend to think about proximal situations. Again, safety being my topic, I will take an example of road accident. When the road accident happened, what is the first thing that you think about? Maybe the driver behavior, because that's easily observable. It happened right on the road. So 1 minute ago, CCTV footage you will try to see and say whether the person was rash driving or not. But do we ever think about the interchange design, whether the design itself was problematic or not, that this signal's design was problematic? It was maybe the previous signal's design that was problematic, and design related decision was done maybe 5 years ago when the road was actually being conceptualized, how this road is going to happen, right? So it becomes very difficult for us to trace the problem because of the delay. This is very, very real, right? So in general, in system dynamics, these feedback loops, the non-linearity of these loops, and then delay can really leave you in a messy situation where you actually end up becoming more prone to just think of short-term solutions and implement, because sometimes showing some action is much more important than the actual outcome, right? Another property that systems follow is conservation laws. Goods quantities are actually conserved in a closed loop system, and things do not just simply appear or disappear out of a thin air. So we actually must understand where things are coming from, where do they go, what happens to the mobile phones when you discard them, what happens to the mobile, where are they coming from, what actually takes to actually manufacture them. Solid waste, where does it really go? Once you burn some part of the plastics, it may actually get converted to harmful gases, landfill piles up, chemical leaching happens. So there's a lot of, it's not like just things went out of your sight and things have been taken care of. They remain in the environment for a long time, sometimes unattended, and that can lead to severe consequences. Pesticides, the primary purpose of pesticides is to kill the harmful, whatever the creatures are which are eating a plant. But what happens to the pest that is dead after eating it? Where does it go? It disintegrates. Perhaps that now that poison is again seeping into your, which is not going to be immediate. It is going to take some time for body to disintegrate and that to come back into your. What happens to the pesticide that is not consumed by the pest? Maybe you put 10 grams. Only 1 gram was consumed by the pest and pest died. What happened to the remaining 9 gram? It is still on the vegetable. It is still there. So if you are not taking into account where is this mass balance equation, and if you do not trace the entire consequences, it becomes difficult. Your system problem will be actually very less defined in that manner, right? So sometimes when we design boundaries, okay, do I care about this? Do I not care about it? Having a good sense of, okay, total quantity of water or the waste that I'm dealing with is maybe 100 metric ton or whatever. So I cannot be just focused only on 10. What is happening to the remaining 90? At least I should know about it. Then take a decision whether that 90 is right now relevant for me or not. But completely not recognizing that could also lead to problem that maybe that 90 was causing a bigger problem rather than the current 10 that you are focused on, which is more visible for some reason, right? So following conservation laws, system shows this property, and if you actually if you conserve the system in that manner, it actually helps you identify certain interesting insights which you otherwise would have easily forgotten about, right? System, as we were talking about, it actually shows something called feedback loops. We call them feedbacks and feedback loops. We describe them. There are two types of feedback in the systems thinking terminology. First is the called reinforcing or the positive loops. Second one are called the balancing or the negative loops. So reinforcing the loops are which actually change in one variable leads to change in another variable, and that further leads to change in the original variable in a positive direction, right? So an increase or reduction in a factor leads to further increase or reduction in the same factor. For example, you had 100 rupees today, you earned interest about 10 rupees, let's say 10% per year. Next year you have 110 in your bank balance. Next year you will earn actually 11 rupees on your interest. Next year you would have 121 in your bank balance. The amount of interest that you are earning is actually increasing, right? So you see this is a reinforcing behavior. Unless you take money out of this particular bank balance, it will keep on growing itself. Each year the bank balance will keep on growing and the amount of interest that you are generating on it will also keep on growing. So this is an example of a reinforcing loop where an increase in bank balance ultimately leads to more increase in bank balance in the future, right? Births and population is also same. When more births, it means the population increases. When more people are there, population is more. Even if the birth rate same, but more number of people will be born, which will actually take it to more number of population in future, right? So these are examples, these are simpler examples of what we call the reinforcing loop. But systems thinking also recognize, we were also discussing about this, the saturation, like potential saturation. The world is actually made up of both type of loops. If there cannot be something which is growing infinitely in the world, realistically it's not possible. There are always something that can counter that behavior of growth, right? So these are called the balancing loops, where an increase or a decrease in a factor actually leads to reduction in that factor. For example, when population increases, the deaths also increase. But when deaths increase, number of people actually becomes less. So an initial increase in population leads to higher deaths, that leads to slightly coming down. So it's like a keeping it around a constant or some sort of a goal, right? Keeping in the check, right? In the previous example of bank balance, your bank balance could be directly related to your work effort, right? Suppose you put high work effort, your income goes up, and that leads to higher bank balance. But then maybe you don't want too much rich. Maybe you also want to enjoy other aspects of your life. So if you have too much bank balance, then you are okay. You perhaps don't want to increase the work effort further because you care about other things. He was motivated by a lot of other factors in his procrastination story also. You could derive satisfaction out of doing things beyond work, right? So maybe beyond a point, increasing bank balance is not going to increase your work effort. So this is like, okay, I have reached a saturation. Maybe $1 million is enough for me in the bank account. Is it enough for people? We don't know. But you can understand. Of course, this is a very individualistic example. Maybe a lot of rich people won't know or this behavior, or they won't agree to this behavior. So it's not generalizable, but you get an idea of what the feedback loops I'm talking about, right? System properties. Nonlinearity is a very interesting property. Nonlinearity means that suppose there is a cause and there's an effect. So 1 unit of change in cause may not always lead to 1 unit change in effect, right? It could be that change in 1 unit actually leads to 2, or it actually leads to less, or it could actually vary over time, right? So I'll just give you some example here. Your desire to own a car versus traffic, right? Suppose there was only 1 car on the road, and you think that it is easy to drive, right? So you may have this amount of traffic on the road will not be a driving factor for you to change your purchasing behavior of a car. So we are talking about this point here. Now suppose there are 10 cars on the road. Still, it's okay. Although the number of cars has increased, technically the traffic has increased, but you are still okay. It's not going to make any significant difference for you. So you still continue to desire to own a car because it still makes sense. It's not having any different. Perhaps even when there are 50 cars on the road, you will still be able to find your way very easily because the 50 cars are very nicely distributed. The capacity is good enough for the system, and you continue to have a high desire of owning a car. But when this traffic becomes 1,000, this is where you realize that, oh, it's impossible to drive a car in the city. Why do I need a car? I can maybe just use a normal other transportation mode. So although the traffic was increasing all the way, your intensity or your desire to own a car was not always decreasing. It remained constant or more or less constant for some time and then showed a sudden decline, right? Do you think this is a realistic behavior, right? So it's not always your desire to own a car is continuously going down. It's not like that. It's plateaued and then it suddenly goes down, right? Similarly here, do you know what is irritant? Maybe like, let's say an example of chemistry lab, 12th class, sulfur experiments, making a lot of fumes, right? Still getting headache. So when the irritant just starts, very small quantity makes you irritated and your anger level is going up. Beyond a point, you are so used to it. The smell has become part of you. You have become part of the smell or whatever. Beyond that point, even if the concentration is going below a point, beyond a point, you don't care and you have accustomed to it, you have adapted to it and things like that. So this is also an example of non-linear behavior. In procrastination related example, there is generally this, I teach this in my class also. I've always difficulty pronouncing this name, but something called Yorkes-Dodgson law or something, which says that your productivity versus production pressure. So this is your productivity versus the pressure that you have. When you don't have any pressure, when there's no deadline, your productivity is not very high. So to a certain extent, you need a pressure. But when you are always under pressure, then you are constantly worried, fatigued, and then your productivity also declines. So there is a non-linear relationship between your productivity and your pressure. Some amount of pressure is needed, not needed. Why is it important? Because it is important for you to know what could trigger sudden changes in the behavior. if you look about this example, just before this point, everything, when you are increasing pressure, productivity is going up. So life is good. As a manager, you want to pressurize your workforce more and more and more because they are becoming more and more productive. Suddenly, when you are beyond this point, your productivity is going down. But as a manager, what is your response? What should be your response? Historically, you have known that increasing pressure increases the productivity. Oh, somehow my workers are not as efficient. Let me put more pressure on them. And you actually push them away, keep on pushing them away. Because this is the past behavior that you know. So knowing this actually creates something called tipping point, beyond which the system can showcase drastically different behavior, and therefore non-linearity becomes very, very important, right? This is why always trusting on history is not a good idea. Developing systems understanding is something which is important, right? So just to, this is also an important part of it. And all of this actually leads to situation that when you feel that why is change so hard? So every system has actors, they each have their own goals, aspirations, behaviors. Some people will try to change the system in one direction, other will either agree to it, so they will go along with it, or they will actually try to maintain that, no, I don't like this change in the system. And a lot of people don't understand why this is happening, why these things are even getting changed, why I'm getting affected. And all of this actually becomes very, very problematic for people, and people therefore end up remain comfortable in the location that they are. And there's always very much resistance to change, right? And this is why a lot of well-intentioned public policies also sometimes fail, because they do not take into account how different people react to it. And therefore, they end up pushing on a certain direction which is not desirable by other set of people, and that brings it down. And when suppose $1 billion has been invested on a policy that is not working, the support for that policy also goes down, and well-intentioned effort also do not work. I'm going to give an example, although this is not an example of a well-intentioned policy, but just an example of policy resistance. So this is also available in the book called Business Dynamics, which is the classic textbook for system dynamics written by a professor in MIT. He quotes an example of Romanian government trying to improve the policy related to birth control in their country. So Romania actually wanted to increase the birth rate because they were worried about population going down and so many other consequences. So they ended up doing making the contraception measures illegal, or making the abortions illegal, right? They thought that's why, how could we actually make people to have more babies, right? But what it led to is very harmful situations because it was actually genuinely very difficult for families to support babies because the economy was in a really, really poor shape. So people thought that it will be financially very difficult for them to cope up with a new family member addition. And therefore, and now the government has banned all this access to contraception. So they actually resorted to a lot of illegal channels. So a lot of this smuggling started, where from different other countries, all of this started to come. A lot of illegal abortion centers started opening, which were very unhygienic, very unsafe for the women. And the same, and actually that kind of unsafe access leads to poor health of the women who are actually in that fertile age group, and therefore their natural fertility rate actually comes down. So your intention was to improve, and you, without thinking the effect, you have a policy that has completely counterintuitive understanding. And then people feel like, why could government make a policy so intrusive as my personal choices of having birthright or whatever? So, and that actually ended up permanently like have a huge protest against the regime, and even the kingdom got toppled. It's not a modern day, it's about 1600 policy. It's a long back example. So, but it gives an idea that because systems changes are so hard, so sometimes the policies, when they do not do the well-intentioned effect that people are desiring, it actually causes a lot of people to mistrust what is happening, and therefore you actually end up losing support for some good decisions also, right? So this is also a classic problem in systems thinking. So this is just an overview of some of the problems and why do we actually need to think differently compared to the way we have been thinking conventionally. And now we are going to go a little bit more into the technicalities of system dynamics, which is one of the ways to actually model systems thinking. As you know, model is a model in a way that it is not 100% real. It is always made an abstract representation of the system. It is not a reality, right? And this is a challenge with system thinking. And some of the people were asking this question. What will be a good model for Earth? Globe. What is can you model global warming using a globe? No, right? If you want to understand global warming, perhaps you want to understand so many dynamics that are happening, right? But if you end up going by that logic, the perfect model of the Earth would be another Earth, which is impossible to recreate. That defeats the whole purpose of having a model, right? So a model is always a simplified version of the reality, right? So it will always not be perfect, but that does not mean it's not useful. And that's the idea that system dynamics borrows, that yes, system thinking is hard, system thinking is sometimes too abstract, but you can still make some meaningful models which can actually make you help guide decision making, right? And models in general could be physical. For example, globe is a physical representation of Earth. At least globe will be able to tell you that Earth is tilted so much, where the relative position of the countries is. So it's useful to a certain extent. It's useful to teach geography to kids, right? Or to adults also. Model could be purely mathematical. A lot of you do a lot of statistical analysis. If I change price by this, what will be my demand of the product, and so on and so forth. Models could be conceptual. They could be just ideas. For example, what he drew on the board was just a conceptual model of why things get affected in his personal life. They could be dynamic or they could be static, right? But the whole purpose of the model is, out of so many complicated things, at least it makes an attempt to make you understand slightly simply. And therefore, of course, it involves a lot of assumptions. Every model will involve some assumption, but at least it serves some important purpose that are relevant to your problem. So this is something that we were discussing in break also. Systems always have to be problem driven, right? You ultimately, if you start making links between A and B and C and D, you will ultimately realize that everything in the world is actually connected with everything else in the world. Is that helpful? Perhaps no. So sometimes you need to draw that this is the problem that I want to solve. In order to solve this problem, what are the key things that are important for me, and something that you try to capture into a system dynamics model. And the purpose of system dynamics model typically is to help discussion, to have certain things as a tool to analyze the decisions, but it's really not a predictive model in that way. In fact, most models are bad at predicting. Why do you think most models are bad at predicting? Not necessarily. When actually modelers make a model about, okay, 20 years down the line, this river will be so much polluted, right? People realize, oh, it's already polluted. Let us do something about this. And then they start doing about it, and in 20 years, that river will not be as polluted as the model predicted, right? Because now people are starting to act on it. So model is also part of the decision-making process. Model is continuously guiding the decision-making, and the decision-making is guiding how the model will react. So all models that way are fundamentally wrong, and predictive actually becomes very difficult in that way. And example of model are, of course, different models. We'll not go into all of them. We will just simply start working a little bit on the type of models in the system dynamics language, right? Don't worry if it is looking so complicated. At least we will try to see some of them. So from decreasing order of ambiguity, these models are noted here. We talk about 4 types of model in system dynamics. First is something called the mental model, which is very deep rooted inside any person's mind, right? It is how you think, this is how you behave, this is how you make decisions. Sometimes even you don't know. These are deep subconscious decision-making rules that are available in the people's mind. Maybe in text, sometimes it could be written or informally present in an organization. An organization does not prioritize safety. That could be their deep-rooted mental model that we always have to push for cost saving, these kind of things. And they could also be very much limited to the part that I'm dealing every day. Not everyone, like as a PhD student, do you think they are always changing the global world problems? Today I come and think about world poverty. No, I come and think about, can I write a piece of paper today so that my guide graduates me, right? So it's about having a very small localized understanding of a system. That's what is mental model. But system thinking is about trying to access these mental model which are in individual group of individuals or organizations, and try to connect them. And by connecting, you actually develop something called causal models, where you develop cause and effect relationships, and you actually develop that across different type of mental models. So mental model of person A plus mental model of person B maybe will result into some cause and effect relationship. While individually they may never care about what is happening to other, but as a system mapping, you try to understand that into causal models. Causal models are again very interesting, very good. We will devote a lot of time to develop them in this class also, but they are limited in a way that they do not provide anything actionable. They are good for representation, they are good for you to realize how complicated the problem is, but they still don't tell you anything actionable. And in order to convert a causal model into something that is simulatable, which can actually drive decision making through some more mathematics, there is an intermediate step called stock and flow diagram. System dynamics particularly assumes that the entire world can be modeled using two types of variables. Either things accumulate or there are flows. Flow as in things that flow. Right? I'll give you examples of that. But again, stock and flow data is still without mathematical equation, and ultimately you need to put a lot of equation in the stock and flow diagram to make them something which is simulatable model. Right? In the papers that we have given you references and what we will be dealing with, we actually started with not this. We had some literature review to access what is the mental model. We developed the causal model, we developed the stock and flow model, and we developed the simulatable model so that you can then drive some decision making out of it, right? Sometimes accessing the mental model for a completely unknown problem becomes the hardest part, right? If something is completely unknown, you actually go to many people, talk to them, and try to understand what is happening. What happens is the ambiguity reduces, and each time, each subsequent stage of the modeling makes it more and more clear. It reduces a lot of unnecessary things. It makes the boundaries more clear. It makes equations more clear, and it becomes easier to explain and debate. It is more explicit, right? In general, here, some example of mental model that we already saw. Professor Mayamura was also explaining about mental models, how he thinks about his problem of procrastination or fatigue or lack of sleep quality problems. So in particular case, in population in a region could be a function of how many houses are available. Is it naturally an attractive, beautiful area to live in? I like Switzerland because of the wonderful scenic beauty. It's a choice that I'm making. Even though it is super expensive, I don't care, but those are the kind of decision. Whether jobs are available, and that's how the population of a region will be driven, right? And then converting this to feedback structures. Causal link, cause and effect relationship, and the feedback is actually the causal model. Then you convert it something in form of stock and flow, where you will see these boxes and some arrows coming inside the boxes and some arrows coming outside the boxes. We will look into them. And then idea is to make them simulatable by putting more data and equation inside them, right? Any questions? Quick questions here? Any doubts? What do you think is the hardest part? Can you make simulatable model without this? You can. It will be very bad. you always can. But do you think there is worth of just making this and not this?
There is a worth. Like it will help us understand, but in not that detail.
Yeah. So it will help you qualitatively understand, intuitively understand, but intuition can be wrong. It is not backed by hard data. It is not backed by actual values. So sometimes intuition can also be misleading, but it is good to at least develop intuition, and it is good to develop a common understanding. So there are values of these different models, and we will look into that a little bit more, right? So the part of the course that we are also trying to give you an understanding of where not to apply system dynamics model, because this was a problem with me. When I first time learned about this, I was like, oh, this was such a cool model, started in 1960s. Professor Forrester is an amazing person. Well, he was an amazing person, I'm not denying. And MIT is so cool, and every problem of my life I'll be able to solve using system dynamics. That was the perspective. And I actually have a causal loop diagram of, I made such an exercise on why my long distance relationship was not working when I was in Japan at that one time. And I do remember making like why I'm not able to find effort, time to talk to my loved ones in India. Like I drew a causal loop diagram of this. So it was crazy. Sometimes when you start thinking about it, it becomes too much. But you also have to recognize what the limitation and the strengths of a particular modeling techniques are. And so part of it we will also develop into that. So system dynamics model is not good for getting exact predictions. That is not the power, although it can do. If you have the sufficient amount of data that is required in a system dynamics model, you can actually get good predictions. So it's not that it is limited by the rigor of science or the mathematical foundation. It is not. Most often it is limited by the availability of the data to the extent that is needed in a good quality system dynamics model. And it will become clear why. But so therefore, it's not an advisable, although it gives you some numbers, it is not advisable to use it as a prediction. It is advisable to use it as some sense of what is likely going to happen. Is it going to go like this, or is it going to go like this, or is it going to go like this? Knowing this tree behavior can also become very powerful. Instead of knowing what is the exact value also, that's the kind of point. And the biggest beauty about system dynamics model is it actually allows you to play with the model much more, because the structure of the model is very explicit. So you can do, what if I do this, what will happen? What if I do this, what will happen? What if I do this, what will happen? Through that process, you learn a lot more about how the system is functioning. And that understanding helps you a lot in making better decisions about the system, right? So it's not good at making exact predictions, not because of lack of mathematical foundation, but often because of the kind of modeling challenges that we have otherwise, right? So that is the good thing about system dynamics model. And of course, it helps you develop explicit models that can actually be shareable. You can share with them, you can develop consensus on them, you can talk to about others. Mental models are sometimes very fuzzy, very vague, but system dynamics model become very logical and easy to explain to everyone, right? So that's the whole idea. So one of the first, we are not going to start with mental models because that's a whole different genre of studies. We will start with the second step of the modeling part, which is the CLD, which is the causal link diagrams, right? A part of this example we have already seen. System dynamics typically deals with cause and effect relationship, where a variable is a cause and B is the effect. Okay, causation and correlations, you guys are engineering students, I don't need to re-emphasize on that. So there is a lot of emphasis in the real world to find the causality, okay? And that is still true for this, that you are not absolved just because it sounds very simple or seems like very easy to do, does not mean that you could simply put correlations here. It is still very much a cause and effect relationship. A causes B, right? But system dynamics will always deal with polarity. Polarity means every arrow will have either a plus sign or a minus sign. A plus sign means if there is a plus sign between A and B, it means if A increases, B will also increase. It also means that if A decreases, B will also decrease. Okay? So when there is a plus sign, it means both cause and effect move in the same direction. Both are either increasing, both are either decreasing. When there is a negative sign, on the other hand, in a negative manner, in that case, if there is an increase in A, there is a corresponding decrease in B. If there is a decrease in A, there is a corresponding increase in B. It means the cause and effect moves in the opposite direction, right? Car pollution. When number of car increases, although also second thing is, in a system dynamics model, there will be many such links, many such links. When I am putting links between A and B and making them a plus or minus, I am assuming given everything else in this system is constant, it is only a relationship between A and B. It has nothing to do with everything else. Given everything else in the world remains constant, an increase in A will lead to an increase in B, and an increase in A will lead to a decrease in B, right? Given everything else is constant. That is the fundamental definition. What if you find a situation when increase in A leads to increase in B, but decrease in A also leads to increase in B? Is there a plus minus relationship there? Both have to be true, and then only it is a causal link between two variables. If such kind of situations are happening, maybe you have not captured all variables. Maybe there is a third variable which is also driving the behavior, right? So this is a good test to see that both directions should actually move, and your variable name should also reflect like that. So we'll come to that quality part a little bit. Come back here. Given the number of cars in the system increases, assuming everything else remains constant, pollution is likely to go increase because the emission actually increases, right? And perhaps we are assuming that these are not EV cars or something, or maybe even if it is EV, ultimately the pollution will increase, right? Given the car will increase, the number of train travelers will decrease. Does it happen? Car is more convenient, so people don't prefer, and it kind of becomes important, right? So these are just some of the examples. So then we'll soon do sorry for the trouble, we'll actually soon do a simple exercise to draw causal link diagrams so that it will give you a better feeling, courtesy to my student Dohil here, who has developed an interesting exercise for you. But just few ideas, and I'll not go into details of them. You can easily imagine, and the same problem also happened when he was trying to make the model. It's very easy to define what you defined as procrastination. Somebody might else have defined procrastativeness or something like that. So there is always a quality issue in terms of what is a good model, what is a good qualitative model. So therefore, there are some checklists. We'll not go too detailed into this checklist, but just a basic idea of it. So there are some guidelines that you should be more. Idea is ultimately to be more explicit, capturing these variables rather than making them more implicit and their story is not visible. Using of noun actually make it more explicit rather than using verb or adjective. So trees cut versus cutting trees. Like cutting trees tells you nothing, but trees cut you give you a very good idea that number of trees cut or how many trees were actually cut. So it gives you a very clear, it's very objective number that way. Must be clear and tangible, not vague. So electricity rate is a very clear example. You're talking about a price of electricity versus electricity policy, which policy could be anything, right? So it's not very clear. So these are just examples. Number of buses versus buses. In the previous model, we talked about car leading to pollution. It's actually number of cars leading to increased pollution, right? So that makes it more easy for you to understand. Should have clear understanding of increasing or decreasing value. Sometimes I don't fully understand this point, but it feels that model is more intuitive when you use positive words rather than negative words. I don't know, fully understand that, but I have also noticed that I am starting to use more positive words now. So employment versus unemployment. Maybe it's easy for people to imagine employment rather than describe what is unemployment, negative sense values. Again, profit versus losses. Profits are easy to define because there's a plus minus. Losses, it means that it will reverse, the scale will reverse, right? So sometimes human cognition is also like that. Names must be precise. Satisfaction for whom? Satisfaction of people, satisfaction of managers, satisfaction of staff. So basic idea is to make this variable names actually more understandable and more explicit for everyone. So these are some basic checklists. We will actually, I will leave it with you in the PPT form also. You can, when you do this in your homework exercise, maybe you can refer them back again. But one more important, very important aspect while you are making such causal link diagrams is to make your implicit assumptions more explicit, right? What is your chain of reasoning? Why do you think this is happening becomes very, very important. For example, government employees' morale leading to, if the government employees' morale is actually leading to development outcomes. So for example, if I make a statement, the lower government employee morale leads to worse development outcomes. And why you think why a person's morale is linked to the outcomes. But the reasoning here is the government employee morale is positively linked with implementation and monitoring effort. If you don't have the morale to do stuff, you will not do. So, and when there's effort is not there, your outcomes will also decline, right? So this decreases means this decreases means this decreases. So that's the reasoning to describe it. So make it more explicit, right? Here, another sentence is, if the number of seeds planted on a farm increases, plant height reduces. And if you just make this number of seeds, plant height, people would see why plant height is correlated with or linked to the number of seeds at all. So the idea is the same amount of nutrition is shared among more plants. So if the number of seeds are more, it means the number of plants are more. It means nutrition available per plant is actually less, which means the plant height is actually going to be less, right? So making this chain of thought, mechanism of how things are happening explicit becomes very, very important part. Sometimes it makes the modeler easy to understand and easy to explain their models also. Sometimes it's also important to break the chain into multiple reasoning. So, for example, higher rainfall will improve rural incomes. Why do you think it will happen that increasing amount of rainfall will increase to rural incomes? Yeah, rural income is primarily dependent on agriculture. And how is agriculture related to rainfall? Rainfall leads to irrigation, and that perhaps provides more water, and that leads to more produce of agriculture, right? So that's it, right? But does it, so this is the mechanism which is clear, but does it carry the full picture? What happens when you produce too much? Soil fertility could be low, prices could be low, so your next rural income is actually the total function of quantity that you are selling and at the price at which you are selling. So while this mechanism only talks about the quantity, but actually if your produce is much more, your price of per unit produce may actually go down, and the net that you are is the effect of it, right? So there could be multiple ways the one single link is presenting. So for example, amount of rain will actually leads to high farm output, which output is directly, if given everything else is constant, an increase in output will increase in income. But an increase in output can actually decrease the selling price, which will then further decrease the income, right? So net effect of this variable becomes important because both of them are important for you to communicate. So making your models explicit like that will help you make better models. Ultimately, we are not finding only A causes B or B causes C. We are interested in finding A causes B causes C and how it causes back A, right? Ultimately, in system dynamics, we are really worried about dynamic loops, the feedback loops. And I've given you one example. Let me give you one more example related to high-speed railway. We've already looked at that there are two types of loops. One type of loop is the reinforcing loop, where an initial change in variable in one direction further ends up moving in the same direction, right? So here, yesterday Professor Maimura was talking about how Japanese high-speed railways have been able to increase the service quality, time delays, management of time delays and stuff like that. And one of the idea in time delays is actually the primary delays, right? Which is related to how many times service breakdown happens. And service breakdown is clearly a function of maintenance, how well you are able to maintain. Maintenance is in turn a function of how much money do you put on maintenance, right? Which is actually a function of how much revenue you have and so on and so forth. So the number of passengers have a positive link between passenger revenue. Given everything else, increase in number of passenger will lead to higher revenue. And higher revenue means you can actually put more money for maintenance. Given that, now this is slightly a policy decision also, a company may not willing to do, but I'm assuming here. So there is a positive link here. And once the asset is well maintained, high-speed railway track and everything is well maintained, the quality of service will actually improve, because service will be less breakdown, less issue of delays and stuff like that. And if your quality of services are high, then your number of passengers will increase. So this is a example of a reinforcing loop where an initial increase in number of passengers led to higher revenues. It means companies have more money for maintenance. It means they can provide better services. It means in future more number of people will be interesting to join. Could with this logic, could demand or could ridership of high-speed railway increase forever? He's saying yes. Could it increase forever? There has to be some control, checks and balance. So there is an example of a balancing loop here. When the number of passengers increase, there is a concept called load factor, which basically defines number of passengers divided by number of seats. So it could also mean some sort of a proxy of how many vacant seats are there. Why does it matter to have vacant seats? No. For passengers, why does it matter how many seats are empty on a train? Comfort. To a certain extent, comfort. If it is too crowded, if the train is almost 100% capacity, you feel like, this is not the mode that I want to take. But at the same time, we are talking about maybe load factor over the entire system. So if always trains are always running full, maybe you will not find the ticket that you wanted to take. For example, you wanted to catch 10 a.m. train because that's what is most convenient for you, but it is always full. So you would never have the opportunity to grab the ticket, right? So too much high, like some sort of empty seats actually that way help that even last minute changes can be accommodated and passenger would be feeling convenient. So what happens is when the number of passenger increases, overall congestion in the train increases. That leads to more inconvenience to some of the passenger, and that actually decreases the number of passengers. So there is, every system dynamics model will have some number of reinforcing loop or some number of balancing loops, and that's very, very important. How do you identify if the loop is reinforcing or balancing? Balancing will have odd number of negative effects. So in this case, for example, this variable is a positive variable, this is a positive variable, but this is one negative variable. So this becomes balancing. Here everything is positive, so it becomes a reinforcing. There could be a situation where one of them is positive, two negatives, and one of them again is positive. This would also be a reinforcing loop, because an increase in A leads to increase in B, which leads to decrease in C. But decrease in C actually leads to increase in D, and increase in D further leads to increase in A. So an even number of negative links in a loop will actually make it a reinforcing loop, whereas an odd number of negative links in a loop will actually make it a balancing loop. Engineer's term to quantify this particular thing. Right? So yeah, the key benefits of CLD is that it makes your assumptions explicit, it allows you to challenge others' assumption, it helps you actually find out where more information is needed. You can point out what variables are missing, what more needs to be understood, and you can actually expand. You can think about, okay, I'm not thinking about this. What if I expand this variable more, and so on and so forth, right? So this is a checklist. I'll not go into the details of it, but the idea is we always start with the purpose of model and we read about it. We try to access the mental models. Based on that, we first identify the variables. Based on the text, we identify what are the key variables that we think are important in this problem. Then from variables, you identify the links between them. Links are whether the links have polarities. So variable names we have seen, maybe A, B. Links is that A actually is linked to B. Polarity means that you have either defined plus or minus for B. So this is a systematic process. And then ultimately we actually try to identify, are there loops in this? So could there be a relationship between A, B, C, and there could be a feedback. And sometimes finding the feedback actually becomes the most, that it's not a straightforward process, but you need to think, could there be a relationship between C contributing back to A and things like that, right? So let's, I'll not make it too complicated for you right now. I'll just leave it here, but I want to do an exercise of developing a CLD exercise. So just to summarize, world is interconnected and textual description often makes it very complicated to communicate how the world is communicated. So we actually develop CLDs to make it simple, make it easy for people to talk about it each other, shows what exactly this is. But the biggest problem about CLDs is they cannot be simulated and therefore they're still limited. They're good, but they're not 100% there. So we will do an live exercise, maybe in groups. I think I have naturally 2 groups. 2 groups is fine. There's no problem. We need not. If Arif wants to be part of it, for sure, but up to you. So I've already mailed you this link, the information, but there's also a class sheet which you can read. Maybe spend some 10 minutes on this. We have to follow. What we have done is, what Dohil have done is, I have made him do is, essentially just look at the random quotations about high-speed railway demand on internet. And these are some quotations related to different types of high-speed railways in the world. These are not necessarily taken only from India, only from Japan, or these are everywhere in the world. Assume that they are applicable everywhere in the world. So just because the quotation says that it only happens in China, you can safely assume that it happens everywhere in the world, right? Just for the sake of this exercise. And what we have done is these quotations we have taken that will help you make a model related to demand. Some variable it will help you identify related to passenger, how many people are going to travel to high-speed railway. I think you also did this slightly thinking about the demand factors, so that yesterday's exercise will help you. So what you have to do is spend some time reading this first. There are some, I think 8 quotations or 9 quotations, 7 or 8 quotations. From quotations, you need to find some variables. Could be 1 or 2 or 3 variables from each quotation that you think are important. This is not an individual exercise, by the way. You can read and do it in a group. From variables, you need to find the links between them. Variable A causes variable B, so causal links. From links, you need to find the polarities. Okay, and then from polarities, you need to find whether there are any loops. And then identify whether there are reinforcing or balancing loops. Okay, so right now we are about 5:02. I'll give you 10-15 minutes, and then we will have a discussion on that part again. Maybe 10 minutes. Again, not an individual exercise. You can do it in your groups. All right, let's start. There is, of course, we are constrained by time. But the first question that I want to ask you, is any of the quotation out of the ordinary, like, or do you believe whatever is happening? Do you understand and do you agree that these could be real quotations, or these are ChatGPT output? Bharvi says that you don't believe. Which quotations do you don't believe? No, okay. So, but ultimately it talks about the concept of when the demand is high, you lower the price or whatever. Demand is high, price changes. That kind of dynamic pricing is, but that construct you agree. Whether it happens on Monday or Friday is not a question. That depends on the context. Yeah. Okay. All right. So let's look at it. What are some of the variables? Don't go like full list. Just give me 1, 2, maybe this group, 1, 2, maybe this group. Yeah.
Okay. From the first quotation,
Let's not worry about individual quotation. Just give me a couple of variables.
travel time,
Of what?
travel time of person.
Person.
How much
Trip time of HSR. Okay. What else?
Frequency of trains, frequency of HSR,
HSR trains. Okay.
price of each trip.
frequency of trains, price as in the price of high speed railway ticket.
Price of speed, right?
Yeah, basically HSR ticket price. Okay. And then
Number of passengers.
number of passengers is that you are something trying to model. Okay. And
Population of the city.
population of the city. Okay. Where did it come from?
Speed of HSR.
Speed of HSR is a variable. Okay. Yes.
And services provided.
Services as in frequency, quality, Wi-Fi,
Quality. Quality wise, right?
quality of service, speed, everything together.
Overall service.
So level of service in HSR trains, is that a variable? So everything, service reliability, everything. So goods quality service. Okay. So let's put it somewhere here. Service of HSR. All right. What else? Anything missing? Sustainability. There is a comment on sustainability. Okay. Let's look at that. Oh. Sustainability of what? How is it defined?
Sustainable infrastructure that whether
What is sustainability? Is it about CO2? Is it about number of people traveling? Is it about money
CO2
saving?
emission actually
CO2 emission of what?
means in it with respect to the other mode of transport.
Okay.
Means each person CO2 means how much equivalent CO2 they are emitted in this much kilometer
Okay. So CO2 emissions
per person
per passenger.
per kilometer.
Yeah, that's okay. Of HSR versus other.
Other mode of transport like car and aeroplane.
There's a single variable that captures everything. Okay. All right. What else?
Mode of travel.
How is mode of travel a variable?
Could be HSR or fly.
What value could it take? Mode of travel.
Three variable but not variable.
So then yeah, a variable means it has to be then quantifiable. It has to be take some value.
Attractiveness to avail HSR.
Attractiveness to
Attractiveness to avail HSR. So there is this, it can shift travelers' habit away from planes and cars to HSR. And one
so that is what? Competitiveness or relative willingness to choose HSR. Okay. Willingness to choose HSR. All right. So this is a attractiveness for a passenger for HSR. Is that what you mean? Okay. What else?
Number of people migrating.
Migrating. Where? Population and number of passengers. We have two variables already. Are they covered?
Rate of migration.
Yeah, but
But
migration
what is
is
migration? Who is migrating where?
to city, to the prime city.
Commuting or migrating?
Commuting is a different.
Okay.
Migration
Number of
is
people
a,
starting to come in city.
Yeah,
Okay. So,
so-
inflow of migration, let's say. Okay. Interesting. What else? Is it? Service quality is maybe in service of HSR. We have captured it. Okay. What else? Things reasonably good. Okay. Are there links? Of course. Stupid questions. Silly me. What are the links? Now, forget about what you have written. Now, develop links on here because otherwise it will become, oh, I have a link here, but this person has a link. That's now we have already standardized for the class. So, give me some closest link. Speed of HSR is linked to what?
Time.
Trip time of HSR. Okay. Positive or negative?
Negative.
Speed increases, time increases,
No, decreases.
decreases. Okay. What else? There's only one link. Trip time and frequency is? If trip time decreases, frequency of trains could increase. Why? Same train can come multiple times. Is that mentioned here?
That is something different.
Yeah, I understand. So there is a, I'll put it as a potential link, but right now I am not sure if that is purely from this data or not, but okay, point well taken. But is frequency related to trip time? Is frequency of high speed railway related to trip time? Not at all. What is the trip time? It is related. Metro people are like, how come it is not related? Yes, tell us how it is
So
related.
because to maintain the time headway,
Ah,
so this trip time will be related to frequency.
no, that is you have
How
gone
to
technical.
explain?
Yeah, so that you have to define. What do you care more? Do you care about the trip time or do you care about the total travel time?
From our group, we thought of travel time.
Travel time is a better variable. That's how the process goes. So we are travel time, we are revising it. That's fine. The speed of HSR and travel time still have the same causal link. No problem. Okay. How is frequency related to travel time? High frequency, low waiting time, that will reduce the total travel time. So there is a causal link between this and this, which is negative. When frequency increases, that through waiting time. I am just for simplifying, I am just putting it here. Okay, cool. So Kunal, can I remove this dotted arrow now? Because now we are talking not about trip time but travel time. I understand it is related, but it is not directly there. Okay. What else?
Waiting time is lesser, service of HSR will be
Service is very much related to quality of service, how people perceive about it. Yes, to a certain extent, if waiting is not, it could be a perception. And that's why I hate the variable name service, because it's so inclusive. So either you define, but I think the way they conceptualize it was reliability, punctuality, that is not related to waiting time.
Service and number of passengers.
Frequency and number of passengers are linked. Why?
Through the service.
Through frequency and HSR are linked through service. Why? Give me the mechanism. Frequency of trains leads to poor service, that decreases the number of passengers. Why do passengers travel high speed railway? Why do passengers choose any specific transport mode?
Good service.
Good service. Yesterday was the good service the first priority? Travel time. So there has to be a link between travel time and your number of passengers somehow.
But when the frequency of train increases, also passengers will increase, right, sir?
Why am I asking?
Because they are intended to travel in that, and because the travel time is also less.
Yeah, so
Maybe
travel
it is
time less we have
three is
captured through this.
interlinked.
We have already captured travel time effect. Is there any other effect that we are missing? Is the question. Direct effect of frequency of train on the travel time we have captured, and that will lead to passenger. We have captured that mechanism. Is there a direct link between frequency and number of passenger which is not captured in this mechanism is the question.
So number of passengers to frequency of train. In case there are more people, demand is more than we
Then?
there should be more of trains running to
Okay, so number of passenger may actually lead to
demand, and then
higher frequency.
to demand, to meet that demand we will
Now, is this a link described or this is a link you are assuming? It's kind of assumed. Let's say it is assumed right now, and nothing wrong in that. I'm not relating it. I'm just saying that it is not directly inferred from the data that you had. Okay, ticket price and passenger are linked how? If ticket is high, then decrease. So this is a low. And here, if the travel time was high, the number of passenger goes decreasing. Okay. So you have first loop with an assumed, which is correct in this case, but you have a first loop. Your travel time of HSR reduces, so there is this negative, positive, negative. So is this a reinforcing loop or a balancing loop? Frequency of train increases, which reduces the travel time, which increases the number of passenger, which further increases the number of frequency of the train. It's a reinforcing loop. Sorry, my R has gone bad. Okay, what else? At least one balancing loop we will try to identify. Population of city and number of passengers are directly linked. How?
Because if the population of city is more, then number of passengers getting.
In Chennai, population is increasing, but there is no high-speed railway. So,
At least people will travel more.
okay, the demand for travel will be high, and she is mentioning willingness to travel.
Is also going to increase the number of passengers.
How is willingness to choose HSR going to depend? What are the functions? Yeah, so that you have already taken into account. So essentially, actually this variable is part of these links that you have directly drawn. Willingness is actually a concept, we'll define it more mathematically tomorrow, but ultimately it's a combined decision of time saving versus the amount paid. A combined decision of that is shown into the willingness to pay. So this is already done. Population of city, driving number of passengers, possible, because travel demand may increase. So that's a possibility. I'm drawing it right now. Let's say plus. What else is there? What is happening with CO2? Willingness to choose HSR and CO2 emissions. This is happening why? Be willing to go. Why? Because people are environmental conscious. Are they? It's not mentioned here. Gen Z perhaps is. Okay.
One variable is investing is like we have mentioned here.
Investing.
But if that variable we have mentioned that we have to
Okay. Is there any
investment in HSR if that was the variable.
Mm.
then
so investment is also somewhere there, which is fine. Good. Is there a link between number of passenger and ticket price?
Yeah, through service we can.
affordable price,
Uh-huh.
there will be more number.
So that is clear. If ticket prices goes up, passengers goes down. But decision to increase ticket price, is it influenced by passengers? Services also. So there is a weekend demand is kind of thing that has been mentioned. So the decision to change price is also a function of what is the current level of demand, right? And here actually it is it a balancing loop or a reinforcing loop? Yeah, so number of passengers are high, ticket price will increase because people would want to bring the system to normal level. When they increase the price, actually the number of passengers. This is how they try to moderate the crowdiness of the site. So you have identified another balancing loop. I'm really impressed, by the way. In 16 minutes, you have been able to identify one positive loop, one balancing loop, and very interesting Gen Z factor of willingness to choose of CO2 emissions. Do you care about when you choose a flight? Do you care how much CO2 emission is the flight making?
Some apps now show.
Google shows, but do you care?
We look into pricing.
We look into the time at which it is leaving. Do I want to reach to US at 4 a.m. or do I want to reach US by 6 p.m.? This becomes an important aspect. Although it will show me so many gigatons of CO2 you are going to consume, but do I really care? Maybe not. So, but yeah, this is a very interesting aspect. Availability of this information could trigger change to certain people. How prevalent that is, something becomes very interesting. A lot of the new generation actually demand this information more and more. And traditionally, this was not included in a lot of demand prediction models, but now this kind of information is actually becoming more prevalent. Yeah.
corporate travels like business travels,
Mm.
so who are contributing towards the sustainability.
Yes. So people who, the businesses who want to show them that they are actually doing a lot of effort to improve sustainability, they may actually take into account how much travel are their employees taking. And I think in University of Tokyo, there was a policy once, right, that you are not allowed to take morning flights or evening flights because there was some expensive, at least for students there was. Once I had booked tickets, so there were specific guidelines that typically these indirect flights versus direct flights, they emit more CO2, blah, blah. It was not inspired by CO2, but some guidelines were there. So you could actually control that maybe employees are not supposed to take indirect flight. They are only supposed to take direct flights, or it even matter, no matter what the price is and all. Also, these kind of policies could come. So interesting. At least the purpose of this exercise is solved. You have been able to identify one reinforcing loop and one balancing loop. And there are more still, like this investment related business is also there. There is actually another possible loop. If more number of people start using high-speed railway, there will be more investment in maybe capacity expansion, maybe service expansion, and that will actually further have a more positive enforcement on this, right? So, hope this was an interesting exercise. One thing that I wanted to highlight was you guys were natural in it, but there is always this idea of some assumptions. We quickly went beyond what was strictly mentioned in the data. And that's the beauty. That's actually is needed to happen. That data will capture some things, but then you need to question, could there be a link between them? Could there be a feedback loop between them? And like explicitly and extensively looking for feedback loops is what makes a causal loop diagram more interesting, because then you are questioning, hey, could this actually change this, right? So for example, in the previous analysis that you did, you stopped at procrastination, but you did not start thinking, okay, what happens if I do procrastination? Is the quality of my assignment good? Am I getting good marks? Will that change me in future? Will I keep on doing procrastination? Because people are able to change their behaviors, right? I make a hasty submission. I know I'm going to get poor marks. So I know that, okay, next time I'm not going to repeat this. So the feedback thinking becomes very important. Sometimes you have to deliberately look for them. That does not mean that you start making feedback loops just for the sake of making. So there's a right balance between, so far you were relying on the information here, assuming it is true, to come up with links. Now you are testing whether there could be more links that will result into loops, but each of those things you need to validate. Then you need to validate rigorously. Is it supported by more information and more? So what starts with 7 quotation will ultimately result into a more comprehensive diagram and even more number of quotation that you will find to back this up, right? So that's how this modeling exercise typically go. So I'm really, really happy that at least you were able to identify one reinforcing and balancing loop. Dohil had also prepared a solution, which I will leave it to you, more or less yours, similar. He had a congestion, travel time of other transport mean, high-speed railway travel time, and the time difference between them will actually derive the number of adopters. The number of adopters and the pricing and that is the balancing loop that he was able to identify. This investment in the high-speed railway was that he was able to identify. But you guys are able to identify a much more cooler one. This is a direct loop between frequency, service and all based on an assumption that you did. So good job there. All right, so this I will leave here. Now maybe we have just half an hour. I'll quickly go we have looked at causal links, but ultimately system dynamics is not only limited to causal links. It's actually to convert a model to something simulatable. And when you try to simulate things, the first and fundamental concept here is stocks and flows, right? So system dynamics assume that the entire world can be made of just 3 types of variables. 2 of them are fundamental, stocks and flows, and 1 is more auxiliary variable, which is just a relationship. A simple example of stock is this here. Suppose you have a water tank where some water is coming out and some water is coming in. Amount of water in the tank at any point of time t, or the height of water in the tank, is stock. It is accumulated. Outflow is measured in meter cube per second. How much volume of water per second or per hour is coming out of the tap, versus again how much volume, how much quantity per unit of time is actually coming in the tank, right? So the amount of water in the tank at any point of time will accumulate based on whatever has been the outflow, the net effect of the inflow minus the outflow, right? So system dynamics assumes that the entire world actually can be developed using a concept of stock and flow. Do you find it believable or no? That The whole world is made of two type of variable, things that accumulate and things that change the accumulation, things that flows. So, for example, population. At any instance, the number of people in the world is the stock, the value of that stock. Births, number of people getting born in a year, let's say. Number of people dying in a year. Number of people migrating from one city to another city in a year. These are all rates that will change the stock of the population. So if you wanted to estimate how many people will remain in a city in, let's say, 10-year time, you need to estimate how many new people will be born in that city per year for the next 10 years. You need to estimate how many people will be dying in that city per year for the next 10 years, and also how many people will be leaving the city or coming inside the city per year for the next 10 years. And if you know all these values, by knowing the value of the number of people today, you will be able to predict number of people in the 10 years from the down. Right? That's the whole idea. Your account balance, your bank balance is actually the stock. It shows you the current amount of money that is dependent on how much monthly deposits do you make, how much monthly withdrawals do you do, how much interest do you earn monthly, how much fees does bank charge in a year to maintain an account. So flows have the unit of time. It's the quantity in stock divided by time, some unit of time per unit time will all be there. Air pollution, the total quantity of air pollution, whatever you define, maybe sulfur dioxide, maybe nitrogen dioxide, maybe PM 2.5 concentration, the total quantity is a stock. What are the sources of inflow of air quality? Exhaust of vehicles. If vehicles, when they burn the fuel, they actually emit some of these things. Wind actually does what?
Transport.
Wind actually takes away, right? So in a particular region, wind actually may take away some of the air pollution from that, some quantity of that. Absorption by trees, is that an inflow or an outflow? Trees will absorb some amount of flow per unit time, so that is an outflow. Industry, is it an inflow or an outflow? Could be carbon capture industry, could be pollution capture industries, those kind of things. So there could be both inflows and outflow. The total garbage on the streets. The inflow is how much garbage is being thrown. The outflow is how much garbage is being properly collected. Garbage eaten. Stray animals, that is a valid outflow in this particular case. The speed. Your current speed is actually a stock. It is a function of how much acceleration you have been doing, how much deceleration you have been doing, how much air resistance, how much friction, all these forces that you are facing, right? So typically, if stock is represented as a function of t, rates are typically ds by dt, right? I'm going too technical suddenly, but I'm assuming that all of you will know this, but this is essentially a per unit time rate of change of the stock is defined as the rate, okay? Is this concept clear? Making sense? Let's see what will happen to the value of stock over time. We are typically,
So is it always necessary to be these rates to be like unit of time? Like,
yes. In system dynamics, yes.
can't it be like, okay, some numbers like?
Numbers could be anything. Units have to be the value of stock per unit time.
Okay.
Yeah, that's what you are interested in system dynamics typically, right? So let's look at this. Let's say I'm interested in plotting how much water is inside in this tank, okay? Suppose your inflow and outflow is exactly same. What will happen to the value of stock over time? Constant. Whatever was the initial amount, let's say whatever h, it will always remain that straight line with respect to time. So this is the line. Suppose your inflow was higher than the outflow. The value of stock will keep on increasing, like it will maybe show a graph like this. Suppose outflow was more than inflow, what will happen? Decrease. Can it become less than 0? In certain cases, yes, most of the time we don't assume stocks which will become negative. So at certain times it's possible, but in general we don't model such stocks, or we put condition that ultimately stock will reach to zero, and beyond that there is nothing happening, right? So yeah, when inflow is greater than outflow, the value of stock will keep on changing for time. When inflow is less than outflow, value of stock will. Most of the time, are you actually worried? Give me an example. Are you actually worried about the total air pollution inside the environment, or are you actually worried about how much air pollution is getting emitted per unit of time? What do you care more about? Health impacts, are they dependent on what? Inflow or the value of stock? Value of stock, right? When you say water is polluted, you measure that stock. Okay, this water is so dirty because of whatever the value is. Do you care how much inflow water is bringing, what concentration of pollutant it is bringing? No, right? And this becomes very powerful message. A lot of time, even in the climate change, this is a very big debate. We think only controlling inflow is good enough to solve a problem. Sorry, when we're talking about the global climate change, it's about the absolute amount of carbon dioxide present in our atmosphere, Earth's atmosphere. When we are controlling the inflow, we are just stopping new emission to come. But we are not doing anything with the existing carbon dioxide that is present in our atmosphere, right? This simple message, very difficult for politicians to understand most of the time, because nobody wants to deal with the existing stock. It's very easy to make policy that no new emissions will come. But what about the pollution that already exists? How will you clean it up, right? A dirty river, if you stop all the pollution, yes, it will not get more polluted, but the pollution will not go away still, right? So just stopping the inflow is not sufficient enough to solve the problem. You actually need to open some sort of an outflow to actually bring down the problem a lot more. And of course, sometimes you want the value of stock to be higher. So this decision making will go in the opposite direction also. So it's very important that we often think that there is no new pollution will be generated. So this policy should actually result into most interesting result, but doesn't do anything. Because even though new is not getting generated, what about the existing one getting treated, right? That becomes a very important aspect. So this is the mathematical view. I like this, but I'm not going to force on this. But this is just to show engineer's term. So the value of rate of change of stock is equal to the net inflow minus outflow of the system. So if you know the functions of these with respect to time, you can integrate this function to estimate the value of stock at any point of time. So it's very simple mathematics. This is the fundamental principle behind system dynamics. I'll not go into the details of this because we're not going to simulate, but stock becomes very interesting. So actually stocks provides a lot of inertia with the system, in a way that soil fertility is your stock. New pollutant coming in is actually depleting the fertility, but you may actually do soil improvement, that is going to do. But the new amount that you are referring to, or the amount of money that you are putting on just on improving the new soil, is not going to be sufficient enough to take care of the entire problem that you have done in the past. So today you say, hey, we are planting trees. That's not sufficient enough to counter all the pollution that has already been done in the past. So while you will feel that I'm making so much effort planting trees, nothing is happening. Nothing is happening because history of the stock accumulation has been very, very large. And removing that will take its own time, sometimes there's a natural degradation. Nature has its own way to consume the pollution. Even if you leave the river for 1 year, river has a natural way of cleaning itself, right? River ecosystem is like that. But even then it will take a year. Just because you have stopped today does not mean tomorrow river will look nice. So if you want a nice picture in the photograph, in the newspaper, that today we stopped sewer connection from here and suddenly nothing is happening, this is what creates the resistance. The government has put money to control the sewer network, but Yamuna is not getting cleaned. I'm not saying government has put effort. Besides all the policy, the impacts are not immediate. It takes time for value of stock to come to the values of acceptable, and that is a function of both the inflow and the outflow, right? turning off inflow does not mean outflow will stop. That's also another thing. In this example, suppose you just stop water to come in this bucket. Does it mean outflow of water is going to stop? No, right? Outflow is still coming because there is existing water in the tap, in the whole bucket. If you care about outflow to be stopped, in that case, in stopping just inflow is not sufficient enough. Again, so we have to realize that it takes time to clear off the backlog. Like all those things becomes also important. So these become very interesting. They provide a lot of interesting dynamics. We will look into that as we move ahead. And the beauty of system dynamics is stocks could be everything. There is a stock in this model which name is height. Height increases is the flow. Height decreases is another flow, right? Tolerance, how tolerant a person is. Apparently in this model, education increases the tolerance of a person versus there is a natural tolerance erosion. You become intolerant over natural scenario also. Unfamiliarity. It is how many new experience that you are not familiar with that is leading to a total unfamiliarity versus there is a process of you getting accustomed and that is making you more and more familiar of the situation, right? So you can actually model stocks like anything. That's the beauty of system dynamics. In your previous examples, frequency of trains, which is currently how many number of trains are being operated, is actually a stock. It depends on how many new trains are being introduced versus how many old trains are actually taken away from system, because some of the old trains will have to be taken away from the system for permanently retirement or something. So the number of trains number of services that you can offer right now is a function of new purchases minus the old retirements that you are worried about. Okay? Again, I will not go into the details of this particular case, but in system dynamics, this becomes the golden truth. Value of stock can only be changed by a flow. Okay? This relationship becomes sacrosanct. I will not go into detail. It's very technical modeling exercise. But let us look at some simple examples of stocks and flows. Sorry. Skunk is a type of animal. The number of skunk is stock. The births will become the inflow. The deaths will become the outflow. Amount of plastic in landfill is a function of how much is getting dumped per unit per year. How much more is getting dumped is a stock inflow. Is there any outflow of plastic in landfill? If we clean, if we maybe take away something and do some recycling, perhaps that will be the outflow of it. Does it naturally degrade? Maybe yes, but too slow for the time horizon that you are worried about to have any visible impact on this particular stock, right? Number of trees. Number of trees in the jungle is a function of how many trees are you planting versus how many trees are you harvesting in a unit of time. Brownies in your stomach or the food in your stomach is a stock. It is a function of how much quantity of food are you eating per hour versus how much food is getting digested by your natural processes in hour. And that shows the number of. Why do you want to track how much food in your stomach? This will actually tell you the potential energy that has not been converted yet in your system. And this is when digestion happens, energy also gets released. So this much amount will actually get released later and later and later. So you would be interested in tracking this, and that's again the beauty of system dynamics. Digestion actually converts what is going to be a valuable product for your body to a waste. It also generates waste. Some amount, mass balance is still there. This digesting is not just removing out of. Mass balance is still there. Waste is getting accumulated in your body. But this will tell you how much sugar will get released or how much sugar will convert into energy in next couple of hours. That kind of a tracking could be helpful. Energy resources, especially when you're talking about non-renewables, then total petroleum is actually getting depleted by consumption. Why is there no inflow for petroleum?
Considering that it will take
Millions of billions of years. That's why there is no inflow. It's beyond the humanity time scale. It's not that it's impossible. It has come somehow, but it's in the kind of typical problems that you would be solving. This would not be significant. Does it also apply to renewable energy sources? This kind of a stock behavior? Why not? Yeah. So your consumption is a function of the capacity of infra that you have. That capacity gets added versus some of that capacity actually goes down. Like solar plants, without solar plants, you can't harvest the solar energy. But that plant, the more capacity you can add, how many gigawatt per year India is constructing versus how many of them is getting decommissioned because of old age or whatever maintenance issues and so on. So that will still be part of it. Okay. Number of buildings or sand castles depends on construction, demolition. Why is this dynamics important as a civil engineers? Urban growth, it tells you construction waste, it tells you demolition waste, it tells you the number of buildings present right now and in the future how the demolition rate is going to change, right? So these kind of models become very important. These are seemingly very simple, but actually you just start expanding on what factors will contribute to construction, what factors will contribute to that, and that's how you expand the model. You start with very simple stocks to further develop your model, right? This distance and velocity. Velocity is a flow, distance is a stock because V is ds by dt. We all know this. And then velocity and acceleration relationship is. So system dynamics can actually model your basic physics equations. So it's mathematically powerful enough. It's not that mathematically it is not powerful enough. It is powerful enough. And again, we are talking about time scales. Time scales could be anything. It could be microseconds, it could be nanoseconds, it could be years, it could be centuries. The model is modeling capability is there. You just need to define what is your per unit time, right? Pinocchio's nose. Do you know Pinocchio's story? Number of lies, something it used to happen. So yeah, that's a very simple one. Money in the bank account, we have already talked about. Number of nuclear weapons in the world. Even if a lot of countries have adopted a policy not to construct new nuclear warheads in the world, does it mean world is free of danger of nuclear warheads? Because so much has already been constructed and nobody is disarming them. So while that treaty is good, that nobody new is going to build, does it mean the world is safe from the risk? No, exactly. But politicians want you to believe that the world is now safe in this kind of an environment because nobody is constructing new. What happened to the existing one? Conveniently, people try to hide that, but it becomes very, very important for you to understand this. Right? So yeah, these are just some ideas. Again, we will go into more specific model. We will actually build on this model that you developed today to emphasize some of these concepts, but always keep in mind that stocks will have flows, inflows and outflows, and the relative values of inflows and outflow will actually determine how the value will actually change. So this gives you the power to simulate the model, make the system dynamics model a simulatable one. And again, simulatable model has a lot of advantage, but it is not a good tool for exact prediction. It is good tool for understanding how the system is behaving. It is a good tool to understand what if I do this, what will happen? What if I change this, what will happen? It allows you a experimentation opportunity. Once the model is ready, you can play with the model however you want. In the model, you can kill as many people as you want. No judgment because it's a simulation model, right? But it gives an idea what the world is likely to look if you simulate this in your model, right? So this is the beauty of the model. But yeah, it's not a good tool when in general you are not interested in dynamics. If you are not interested of variable over time, then system dynamics is not a good tool. It is not a good system when only linear systems are there. Some systems do not have a feedback, like very simple machineries and all. So then we don't need to worry about any of those, right? When precise predictions are required, it is not a good approach. And detailed models capturing individual and spatial variation. So you can easily imagine if I were to make a travel demand model considering each person on high speed railway, if I'm trying to model how each person of these 1 million will make a choice to travel into high speed railway or not, depending upon what is their current income level, what is their current geography, and how much time it is going to take, it's impossible. This model will become very crazy. So system dynamics typically considers average behaviors, but it does not model these individualistic relationship, and it does not scale up very well that way. For those, other kind of modeling approaches are there. If you are interested, we can also, not in this course, but I can refer to you more interesting topics on that. So agent-based modeling are good for having more spatial variation or large number of individuals. If you want to capture individual behaviors, these kind of models do not, system dynamics does not scale well. So yeah, this brings us to the end of class in day 3. Day 3, right? Still day 3. We still have quick 4 minutes before we can leave. Yeah, any questions?
Actually, I want to ask about that stock formation. Can the stock can be function of the T1 and T2 or some other variable where multiple inflows and one outflow, or multiple inflows and multiple outflows where like one inflow is function of a T1, other inflow is function of a
What
T2.
is T1?
T1 is kind of a other variable.
Yeah, it's very much possible. Suppose you want to model the urban population. It is a function of birth rate. It is a function of death rate. It is a function of in-migration in city.
Yeah.
It is a function of out-migration in city. Now, birth rate is completely different factors
phenomena.
compared to death rate. Death rate in a city is a function of maybe hospitals, type of infrastructure, all those things. Birth rate is maybe a function of the current quality of life of people. If they are earning good money, it's very much dependent on that. In-migration is a function of jobs. Out-migration is also a function of jobs, but other location choices and all. So each of those factors will be getting affected by variety of different factors, and that's the part.
And stocks will be a function of all the eight factors that we have mentioned.
Yeah.
And while we are calculating the stocks, then integration of okay.
Yeah.
Okay.
Stock will only be get affected by the corresponding flow. Flow can be then affected by many variables. Stock will only get affected by its own variable, its own flow.
Sir, one last question, like agent-based model versus system dynamics. So that debate, like we have assumption that we can trace individual in the agent base, and we can't trace individual in the system dynamic. That will be wrong. Sir, actually, in agent-based model, we also define it goes from a bottom up where micro phenomena is affecting the macro phenomena. So there also we are having some sort of concrete conclusion about the macro phenomena.
Yeah, but in system dynamics, there is no opportunity to trace the micro one. So system dynamics directly simulates only macro. But in agent-based modeling, you could be interested in macro. You could also be interested in micro phenomena. So tracing of both, depending upon what do you care about, is there. But in system dynamics, there is no way for you to go below. There is no way for you to know what individual passenger is feeling, how they are doing. But when you come a bottom up, you are looking at an aggregated value, but you are then maybe interested in individual passenger behavior or a cohort of passenger behavior that you can do much better. Yeah, we can take it offline also. There's a huge amount of literature written on how are synergistic versus differences between agent-based model and system dynamics models. Yeah. Good. Anything else?
So you mentioned 3 things: stocks, inflows, and auxiliary variables. So what are auxiliary variables?
Auxiliary variables are sometimes one flow will be affecting another flow directly. We will look into some examples of that or some conversion factors and things like that. We will look into that. Yeah.
So things which are the variables which are affecting the rates,
Mm.
aren't those the auxiliary variable?
In a way, yes. Yeah.
Okay.
Yeah. But you're right. Ultimately, they are the auxiliary variables. But then they can be of different type, constant, changing over time. Many things can happen. But they are auxiliary variables.
Thank you.
Good. But is it clear? Is it too complicated? Basic. Tomorrow, when I draw this, you will be able to understand what I'm drawing. And if I draw this and draw this, you will be able to understand what I'm trying to draw, right? Inflow, outflow, stock. Yes. See, this course is not about giving you the mathematics background on this. This will be difficult. But we will give you the model and we will play with it tomorrow. And then beyond that is up to you. How do you want to take it forward? Okay? All right. So to see you tomorrow then.